Ever wondered why the normal model is a crucial tool in understanding data distribution? Well, let's delve into this. The normal model, also known as the bell-shaped curve, is a fundamental concept in statistics. It's a powerhouse tool used in predicting patterns and making sense of large data sets. Imagine having a vast amount of data points and needing to understand the general trend or pattern. This is where the normal model comes in handy. It helps us visualize and understand the distribution, the highs and lows, the peaks and troughs of data sets. It's like a roadmap guiding us through the data wilderness, showing us where most data points cluster and where they thin out. So, whether you're a researcher studying climate change patterns or a marketer analyzing customer behavior, the normal model is your best friend. In the next few minutes, we'll dive deeper into the normal model, standard deviation, and Z scores to shed more light on this fascinating topic. So, what exactly is the normal model? Well, it's a concept in statistics that represents a distribution or a spread of values. Think of it like a bell-shaped curve where the highest point of the curve, or the peak, represents the most frequent occurrence. This point is known as the mode. The normal model is symmetric, which means if you were to draw a line down the middle of the curve, it would be a mirror image on both sides. This line you've just drawn is also the mean of the distribution. In a normal distribution, the mean, median, and mode are all the same, and they all fall right in the center. Now, the normal model isn't just a pretty curve. It's a powerful tool that helps us understand and make predictions about data. It tells us how data is spread out around the mean and how much variation there is in the data. For example, if the data points are tightly clustered around the mean, the curve will be steep and narrow. But if the data points are spread out, the curve will be flatter and wider. The normal model also gives us a way to quantify the likelihood of different outcomes. For example, we can use it to answer questions such as, what is the probability that a randomly selected data point will fall within a certain range? This is incredibly useful in a wide range of fields, from economics to psychology to meteorology. One more thing to note about the normal model is that it's a theoretical model. That means it's an idealized representation of a distribution. Real-world data might not always perfectly fit a normal distribution, but many datasets come close, and the normal model is a useful approximation. Now that we have a basic understanding of the normal model, let's move on to standard deviation. Standard deviation sounds like a complex term, doesn't it? But it's simpler than you think. Let's dive in. Standard deviation is a statistical measure that gives us a sense of how spread out numbers are from the average, or the mean. When we talk about the mean, we're talking about the average of a set of numbers, right? Well, standard deviation is like the mean's bodyguard. It's there to tell us how much the data in the set is varying from that average. Imagine you're measuring the heights of a group of people. The mean height might be 5 feet 7 inches, but not everyone is going to be exactly that height, right? Some will be taller, some will be shorter. The standard deviation is there to tell us about that spread of heights around the mean. In the context of the normal model, or the bell-shaped distribution, standard deviation plays a vital role. It helps us understand the shape of the distribution. If the standard deviation is small, the bell curve will be narrow and tall, indicating the data points are close to the mean. On the other hand, if the standard deviation is large, the bell curve will be wide and short, indicating the data points are spread out from the mean. This measure of spread is incredibly important in statistics and data analysis. It helps us understand the variability in our data. The larger the standard deviation, the greater the variability, or the wider the range in which our data points fall. The smaller the standard deviation, the less variability, or the narrower the range. In essence, standard deviation is a key player in the normal model. It's a numerical value that gives us insight into the variability or dispersion in a set of data points. It helps us make sense of the spread of data around the mean in a clear, quantifiable way. So, standard deviation helps us understand how much data varies around the mean. Next, we'll discuss Z scores. Z or Z scores might seem intimidating at first, but they are a fundamental part of understanding data distribution. Let's kick off by defining what a Z score is. Picture it as a mathematical tool that tells us how many standard deviations a particular data point is from the mean or average of the data set. The beauty of Z scores is that they are measured in standard deviations, which means they are unitless, making them perfect for comparing data points across different distributions. So, how does this work? Let's say we have two students, one from school A and one from school B. Both students have differing test scores, and both schools have different averages and standard deviations for their test scores. How can we compare these two students fairly? Enter the Z score. By converting each student's test score into a Z score, we can accurately compare their performances, regardless of the different averages and standard deviations at their respective schools. Now, let's get down to the brass tacks. How do we calculate a Z or Z score? It's simpler than you might think. Subtract the mean of the data set from the data point you're interested in, then divide the result by the standard deviation of the data set. This will give you the Z score. For example, if a student scores 75 on a test where the average score is 65 and the standard deviation is 10, the Z score would be 1. This means the student's score was 1 standard deviation above the mean. If the Z score was negative, it would mean the score was below the mean. Z scores aren't just for comparing test scores, though. They can be used in a wide range of fields, from healthcare to finance, to compare data points and make informed decisions. Z scores, thus, enable us to compare data points from different distributions. Now let's summarize what we've learned. We've covered a lot in this video, so let's take a moment to summarize. We started off with the normal model, a bell-shaped distribution that's common in statistics. This model is incredibly important because it's pervasive in nature and in data we encounter in everyday life. From heights to test scores, the normal model is a crucial tool in understanding how data clusters around a mean. Then we moved on to the role of standard deviation, a concept that can seem daunting, but is in fact a very handy tool. The standard deviation is a measure of how spread out the numbers in a data set are. It's an essential part of the normal model, helping us understand how much variation there is from the average. A small standard deviation indicates that the data points tend to be very close to the mean, while a large standard deviation indicates that the data are spread out over a wider range. We learned about the 68, 95, 99.7% rule as well. This rule helps us estimate the percentages of data that lie within 1, 2, and 3 standard deviations from the mean in a normal distribution. It gives meaning to the standard deviation and helps us understand where most of the data falls. Finally, we delved into Z scores, which are standardized values that help us compare data across different distributions. With Z scores, we can determine how unusual or typical a data point is within a distribution. It's like giving each data point its own GPS coordinates, letting us know exactly where it stands in relation to the mean. All these concepts, the normal model, standard deviation, and Z scores, work together to help us interpret and compare data. They're not just abstract mathematical concepts, but practical tools that shed light on the patterns and behaviors hidden within the numbers. With these tools at your disposal, you're now better equipped to understand and analyze data distributions. Remember, statistics is not just about numbers, it's about understanding the story those numbers tell.